And actually, on this webinar, we will be talking about the advanced threat evolution and why the Hunting UEFI Firmware Implants is important. And before we start, I want actually to make a quick introduction about the training. So actually, my introduction already happens. I will skip it. And so how we got this idea with my friend Alex Gazette to create the training about evolution of persistence technique and actually how hunt UEFI firmware implants. Basically, both of us was doing research on the UEFI firmware space quite a while, and we see a lot of gaps in the threat modeling and understanding of reality, how this kind of threats is infecting infrastructure and how security products currently exist in the market actually can detect it and don't gain any visibility on these kind of problems. And even some of antivirus products try to claim they can dump and analyze the BIOS. Problem is, without any hardware background and firmware background, it's hard to analyze correctly. And even if you have a lot of data, it doesn't help much. So our training try to fill these gaps, and we're starting actually with some of the things working on the boot sequences. We will be talking about the bootloaders on operating system like Linux and Windows 10, rats and builds. We will be a bit cover the legacy threats like Bootkits and Rootkits infecting master boot record and volume boot record. And also we will be transferred to new threat attack vectors, which is affecting the secure boot. We will be talking about multiple components across the platform like a TPM, BMC, and embedded controller, and of course the BIOS. So what is the difference between our class and others? We actually will be focused a lot on the reverse engineering parts, how you can try to understand where is a malicious code, where is not. And actually also we will be focused on how you can reconstruct your IDB, how you can basically add in your IDB information regarding UEFI specifics and how you can make your code more readable. Okay, let's start a bit why is important. So actually the trend landscape which we see in right now, it's pretty much looks like an iceberg. So the top level of the threats, like threats which is operating on operating system level, we see pretty much well, because it is a lot of years the security products evolved on this direction and they do their job well. But we have also underwater part of iceberg, and I would say it's about modern persistent techniques, which is tied to the hardware and the firmware parts. And nobody, or like very rare, when security products can check this kind of parts correctly. And even if you have the agent on the operating system level, that doesn't mean you will be catch the threat, because if the threat inside your firmware, it can fake a lot of things and even disable the agent, which will be not able to dump or like get any information regarding malicious content inside the BIOS. So let's talk about the evolution of persistent technique. And actually, nowadays we have a lot of mitigations against persistence on the boot process. I mean, like we have a secure boot, we have like a measured boot, we have a DRTM, CRTM, a lot of features built by vendors like Intel and AMD and others. But mitigations actually against the malware persistence mostly raising the bar of complexity in the way when it's cover only the common ones, but not cover more advanced ones because it's not very feasible with modern security products. And if we look how the rootkits evolution happens, it was always basically tied to the hardware. So rootkits on operating system mostly been gone to the bootkits when the code signing policy for the drivers on Windows operating system appears. And when secure boot been introduced in Windows 8, mostly bootkits being gone to the BIOS implants direction. But of course, the people not migrating immediately to a new version of operating systems, and it's take a while. And I would say the bootkits, it's still relevant for many things, includes some of the critical infrastructure parts, which is still use old operating systems or like still use MBR and VBR for boot process. And we will be cover actually all the three parts on our training. We will be talk a bit of rootkits and bootkits tied to the legacy stuff, but our main focus on the BIOS implants and some other things like TPM and BMC threads. So let's talk about the type of persistence. And you know, actually, we have pretty good visibility with modern security products like antivirus endpoints or EDR solutions. But think about, we have a different kind of persistence on the hardware and firmware level. And this kind of persistence doesn't cover much by these products. And it's exactly why we create the training for basically teach you how find the threats, how build the right threat modeling for the hardware to basically acquire new hardware for your data center or for something else, and how basically for big organizations with thousands of computers understand where the risk can be on this side of threat landscape. And if we talk about information of BIOS implants, reverse engineering, or BIOS implants hunting, it's not much. And actually, when we've been writing this book, Rootkits and Bootkits, with my colleagues, Eugene Rodionov and Sergey Bratos, mostly we've been thinking about how this evolution of the persistence threats happens. And of course, we have some parts covering the BIOS implants. And when we was thinking about the cover concept, I was thinking, oh, actually, usual malware analyst or like security analyst in IT security will have zero tools for this kind of threats, and mostly it will be not feasible. And this analogy with Kraken came exactly in this direction because we see on this picture just some really top of Kraken, but it is underwater part which is not feasible. Yeah, and actually it is an analogy which we try to pursue on this cover. If we talk about the golden age of rootkits, it happens like back a while ago. And most of the drivers of this persistence being a cybercrime, when the actors try to persist on the user machine as much as they can, because they need distribute spam or like use infected machine as a DDoS bot. And it's exactly why the rootkits became very popular at the time. But as we mentioned before, when the operating system start implementing some mitigations, development for the rootkits get more expensive, and attackers shift down on the stack. And when basically Bootkits became on more feasible on this scene, it's actually 2011. And I would say mostly in 2015, it's been gone, and it was no actually many machines infected such as threat. So, but also we always should keep in mind about the state-sponsored actors, which is persistent goals is different. And it can sit on your machine for some time for when it will be activated. And it's exactly the thing which is can be used for firmware implants, because it's not visible. You can change your hard drive, you can change your operating system, and malicious code still will be inside. Here's a few links. You can find some samples of malicious rootkits, bootkits, and implants on the GitHub with the samples from the book. But actually, I can say golden age of the firmware and hardware implants is happening right now. And it's happening exactly because not a lot of people can understand and gain the visibility on these threats. And actually not a lot of tools, and actually mostly it is zero tools for hunting firmware implants. And on our actually training, we will be talk about how we can use the common scenarios and tools which is available to combine in some of analysis tool set, which is help you to analyze and catch this kind of threats. But if you look on the retrospective on incidents with the BIOS implants, it was multiple. And probably most recent, it's a low jacks, which is happens last year. So maybe happens not last year, but was detected last year, but by antivirus company named ESET. And it's actually was very interesting, and we will be covering details in our training, most interesting part and how you can reverse engineer this one. But if you look on this timeline, you can see two different ways of evolution. One way, when the researchers basically develop new techniques and detect some ways of persistent and present on the conferences. And we can see a lot of research happens during the time, but also we can see very rare incidents, which is basically happens with a real malware implants tied to the firmware. And mostly it's because we don't have tools and knowledge to catch it. So actually every year number of incidents is increasing, and not only based on real attacks, it's also based on the research with researchers presenting. And we can see clearly this year and last year, board management controller for the servers, it's been really, really one of the top targets. And in our class, we also will be covering this part. This picture, it's actually statistics from National Vulnerability Database. And we can see we have a lot of firmware vulnerabilities every year, but also I don't think every vendor or all of them being reported, and I believe this numbers is much bigger. So basically, we don't have much mitigations which we talked about, and if we look on this picture, you can see OS kernel mode have a patch guard. On Windows operating system, it has patch guard, code signing, and also for prevention, it's multiple endpoints working on there. On the boot code, it's also can detected by antivirus vendors and endpoints, and secure and measured boot and the boot guard try to take care of this part and armoring the secure boot process. But on the BIOS and UEFI, we have literally zero. And it's actually no way for the vendor without any integration with the hardware on the firmware side to gain any visibility or behavioral analysis in runtime. Some of the vendors, like Apple, integrate some kind of sanity checks for integrity. And if you see this EFI check warning on your Apple machine, it can actually say something with your firmware is wrong. And problem here, it's check only integrity failures and some known failures in supply chain, but it doesn't say much about what is the impact are. Same thing with modern antiviruses. When they catch the threat, they say the threat is found, but you don't understand what threat is about and what is actually this malicious code is doing. We will try to fill this gap later in January 2020. So, but what is actually most of the BIOS challenges for antivirus endpoint solutions? First of all, everything can be a fake after operating system is boot. If you have powerful implant inside and the attacker spend enough time for analyze the platform and build some malicious capabilities, it can fake mostly everything. BIOS rootkits and implants can disable any antivirus endpoint solution even before it will be actually executed on the operating system level. It even can just remove, parse file system before operating system boots, remove the components of endpoint. All the BIOS updates can be reinfected during installation process. BIOS updates actually is tricky, and we will talk about this later, because what happens usually, you download your update by agent on the operating system, or you already have the update and try with the vendor tool install this update on your machine. But this update mapping on some memory region, when after reboot, it's read by update code inside the firmware and actually flash to your SPI Flash chip on the platform. Think about, if you have malicious implant, do we can actually catch this event when the platform updating and fake it was updated and not really? I believe so. And one more point, it is no trusted path between any endpoint solution and UEFI firmware exists. It's what only cooperation between firmware and antivirus or like endpoint can help to protect users in reality, because it's all the mitigations and all the things which happens in firmware, it's not feasible for antivirus solution. Basically what happens, antivirus or endpoint or EDR, whatever agent on operating system level is executes, it can dump the BIOS, upload to the cloud or analyze inside the operating system with some pre-checks or rules, but it's only static. So without deep code analysis or without runtime behavioral things, it doesn't say much, only mostly about the supply chain problems. Hashing UEFI drivers or SPI Flash dumps don't guarantee much, because even if you found the integrity problem, you don't understand the impact. So, okay, we have integrity problem because the vendor forgot to update the driver and On some platforms, it's updated, some is not. So in antivirus cloud, you have a collision because part of the update on the platforms from the vendor have a different driver, one other part of the platforms have an older driver. So the integrity can fail inside the cloud because basically same update with the same version of American Medak Trends, as example, will have some of collision. But if you just look on the same platform integrity, yes, it will be actually don't raise the flag. Who guarantees the BIOS updates from the hardware vendor is not infected, right? So because it came from the website, it came from FTP server, or you have an agent which is basically says when the updates appear on demand, says you need to update your BIOS, right? So, and if the vendor hacked like a shadow hammer operation, which we'll cover a bit later, so then you don't have any guarantee. This update came from the vendor, right? And the big blind spot nowadays, it's supply chain attacks, because with the physical access, mostly it's not in scope of the security features or threat modeling, or it's not in scope in many even companies, because think about the way how you get the hardware. It's not like you buy on Amazon and Amazon deliver to you. It can be multiple third parties involved in the process of acquiring the hardware, even for your home office. But for data center, it's much more complex. So other problems in supply chain, so it's microarchitectural attacks. Because think about, even if you have the patch in the site microcode, it doesn't mean your hardware vendor deliver you the most recent microcode update. So if you have a lot of components across your hardware, like USB controller, BMC, it can be different vendors, and firmware is everywhere. For cloud, and not only, BIOS became kind of like a foundation, and it can be broken, then multiple things inside the cloud can be attacked from the BIOS. And it's also tied a lot on the configuration and what kind of memory encryption solutions you use. It's a lot of things involved, but in general case, BIOS very dangerous for the cloud. And supply chains actually became a mainstream, and we can see it a lot. So this actually Lambda concept built kind of like a prototype of the PCI Screamer board kind of a while. I believe it's about 2.5 years ago. It's a PCI board with Arctic 7 FPGA, which can be used for DMI attacks. But nowadays, we have much smaller boards with mini PCIe, which is use the same Arctic 7 and actually became more dangerous because spot this one much harder in your hardware setup. Also, Dmitry Oleksiuk show very interesting attack vector from the system management, from DMA to get in and elevate the privileges over code execution inside the system management mode over DMA, because it is a lot of, it's actually have some time window to do so. And this is design issue. And in many platforms, it's not fixed because it is design issue. So Microsoft developed very interesting concept of device security, and also interesting because on firmware level, they have a visibility actually. They have, you can see here, they have a 3 different Dixie drivers, which is HSTI Silicon Dixie, Platform Dixie, and Result Dixie. They actually check the different things. And first one checks secure boot and signet updates problems. Another one checks the DMA is locked and IOMMU is enabled. They also check the rollback protection, it's enabled. And Result Dixie just collect this information and pack in some telemetry data. So device guard Dixie, it's another one, have a direct feedback loop with operating system device guard component to runtime check the security features and dependencies. It's very interesting, but it have a very limited way to detect malicious implants, because if it's already inside, this don't tell you much. And if it's already inside your firmware, secure boot will be working correctly, but it's broken because somebody can execute earlier on like fake the secure boot enabled. It's multiple ways, and we will be cover everything in January. Some of the vendors like Gigabyte, ASUSTeK, MSI, ASRock, and Samsung, and actually many others, mostly which is don't really target in the enterprise sector. They just don't care about the biosecurity, and most of the even primitive mitigations like BIOS lock or BIOS write enable, it's just not configured correctly. Basically what that's mean, even like from operating system level, you can just install with same update tool what the vendors use, some malicious code inside. On the other side, we talk a lot on the beginning about what the threats are, right? But what about tools and how we can detect it? And honestly, we have really a lot of limitations how we can analyze the platform and catch something in runtime. But let's talk about what we have. So as example, if you catch malicious implant and you need like a dynamic analysis, you have few ways how you can do it. First of all, if you're lucky enough and you're working for Intel and you have like a model for CMIX, it's like a silicon simulator for hardware. So you can basically simulate everything inside the CMIX and pretty much get the same execution flow as a hardware. But of course, if it's commercial hardware, you can have limitations of UEFI protocols which is used, and some of them can be not available on the CMIX simulator. Pretty similar problem on QEMU. On QEMU, you can try to boot the Dixie driver. And actually, when I try to reverse some of the Dixie drivers, sometimes for security research, I try to make the stubs inside the code to don't call unknown protocols or stop them for gain execution a bit further to understand the behavior of the code. But it's limited, right? You can get a limited coverage because you don't have some parts of the code which is not available on QEMU, or you don't know how the protocol working correctly and can't create the right environment for execution. So, but it will be helpful, still helpful in many cases, and it's open source. You can do a lot of different things to create a pretty good environment for reverse engineering. Hardware level debugging like Intel DCI, it's available, but the most of the enterprise platforms, it's locking for production. You can try to reverse engineer them and unlock, no doubt, but it's not always easy way. And executing Dixie driver on non-native hardware, it creates some limitations, the same as a virtual environment or simulation environment. For the boot process, actually, and we will cover this on the training class because we have with the train some agreement for work with their platform to analyze the boot sequence right after the Dixie stage is locked. It's still a lot of interactions with UEFI firmware and bootloaders like WinLoad, UEFI, and others from the operating system level to UEFI when its operating system is boot. And we can see a lot, even when some parts for IOMMU on the late stages happens for the operating system, when memory isolation over device guard is enabled, or like secure kernel is initialized, and it's fun. But also limitations are we just see very late stage of the boot process and mostly the operating system. Welcome to the brave new world. And actually, let's talk about reverse engineering tools. Here is you can see some just general Dixie driver open in the Ghidra. So if you open in the Ghidra, you don't see much because the Ghidra don't have a pre-analysis, and actually it don't spot any kind of like context from UEFI. In IDA Pro, it's built some pre-analysis features, which is actually provide you some UEFI system table and UEFI handles and a lot of some known generic structures. And analyzing in IDA, it's much actually natural and easier for the Dixie drivers and other UEFI stuff. We will be actually talk about the both in our class. We will be talk about how you can use Ghidra, but where is the challenges, how you can partially solve it, and how you can automate in IDA and make your analysis more productive. And if we talk about the decompilation, you can see here is a comparison between IDA and Ghidra. And in IDA, code is much more readable and understandable from the beginning because this pre-analysis. In Ghidra, you have pretty much similar flow. So if you just analyzing the code and you understand what is going on and you already have your point of analysis, it's pretty much enough. So it's not like Ghidra is worse than IDA, it's just about the context which tools providing you. And I hope someday Ghidra will have the same pre-analysis as IDA and then problem solved, but unfortunately not yet. Let's talk about UEFI update process. And actually, it was a lot of publications regarding this stuff. You can see the links below the picture, but in the update process, it's multiple parties involved. As I mentioned before, we have the operating system application, we have the driver from the application, which is try to map in the specific memory region the update image, and also try to trigger a SMI handler responsible for update process. On this level of updates, we have a BIOS guard, which is basically try to armor the update process. And we actually cover this one because on our Black Hat talk this year, we found multiple problems and reverse engineered most of the flows regarding the BIOS guard. It's armoring the SPI Flash, but even on this picture from Intel, you can see we have only covered some of the regions of the SPI Flash, not all of them. And it is a limitation of the BIOS guard because they don't have much secure slots for protecting regions in SPI Flash, and they can't just protect all the range for SPI Flash memory by the reason. Sometimes we have a supply chain problem. And when you need to update on thousands on machine across your enterprise network, the BIOS, you need to disable the boot guard. And of course, you can't go for each machine and do it manually, right? So you need some features, build it in your firmware, but trigger it from operating system to disable the boot guard and actually secure boot too. So we will be talking about these ones too. Let's talk about some automation of firmware updates. And Microsoft actually introduced pretty while ago CFI concept for deliver general updates for BIOS and other firmwares for the hardware components like a touchpad, like embedded controller and others. Problem is, if you look on their SDK on the GitHub, even in the comments, they not mandatory require firmware update to be signed. And the platform doesn't check or authenticate the update. It's just responsible for the delivery, and firmware or like hardware itself should be responsible for the update, which is make some gaps. And also not all the vendors the same, right? Some of them care about security, some of them not, which is create huge supply chain problem. And even unified update process doesn't solve it. Another very interesting project is Linux Vendor Firmware Service, LVFS, which is responsible for pretty much the same thing. And it's fully open sourced and more about delivery than authentication. And recently they start actually doing some supply chain checks, which is, I think, the right direction to go. But let's talk about how many steps you need to gain persistence on the BIOS. And actually, it's not easy. It's actually two ways how you can do it. You can do it as a supply chain with a physical access, if you have a physical access to the SPI Flash, and if like in some environment it can be work, some not, you can just like update the SPI Flash memory with a new BIOS, and then it can boot with malicious stuff inside. But of course, if you have some mitigations like boot guard and BIOS guard enabled, it can be make the way a bit more trickier, but really depends on the particular hardware. But if you want, not like if attacker want remote way to exploit and install the vulnerability, install the implant inside and gain persistent, it can be multiple levels and stages and chains in your exploit involved. So it's start from user mode, probably attacking some of the browser or like Microsoft Office, whatever, but main thing which is pursuing in this way, it is about OS kernel mode. So actually, when the driver is inside the kernel mode, it's need to talk with over the HAL or directly with UEFI services. And then it's probably can attack some SMI handlers in SMM. And if attacker lucky enough and found the vulnerability, which is allow him to gain access over the code execution on some other direction to SMM and deliver the payload on SMM, it's in some ways it can have direct SPI Flash access. But it's also multiple ways, even if you don't have enough permissions from SMM to attack SPI Flash, which we're talking about our class. Also, don't forget, we don't reboot our machines every day, right? or shut down them every day. Most of them working and uptime before new updates come in. So literally, it's about a month. And even if malicious implant don't have the ways to gain persistence on the SPI Flash chip, it can be persist in SMM runtime for quite a while. So it's exactly why the golden age of firmware and hardware implants is happening right now, because you can see the problem is quite big. And why the firmware is a new big vector for the potential attacker? Because in many cases, firmware was not considered as a critical security asset for a long time. And firmware is patchable, which is mean for the hardware vendor, they can fix what all the time, right? So the cost for the firmware update, it's much lower than hardware. And it's exactly why in most of the cases, hardware vendor will be focusing on hardware bugs and problems first, and then they actually care about the firmware. During bring up for the new hardware is very hard. Basically, when you try to boot new hardware the first time after manufacturing, many vendors do the mistakes in misconfiguration because the biggest part they care is boot the platform. And sometimes also they forgot to configure security features back on the production stage. So another problem, everything goes to the cloud, include firmware and hardware. It's most cases cloud providers don't control firmware and hardware, so supply chains attacks became a huge vector for modern attacker. Even isolated VM instances can be attacked too, and persistence in the guest instances can be happens with a virtual BIOS. Let's talk a bit about the UEFI persistence classification. And we have actually two major ways how malicious code can persist. It's result of exploitation and compromising supply chain. Both of them, it's very big vectors and gain a lot of problems for security and CISOs inside the companies, mostly because, as we can see, it's many different ways how you can gain, basically how you can execute implant on the platform. But I would focus for now more on the supply chain problem and look on it. Not all the hardware vendors even have authentication for the BIOS updates. And if we talk about firmware updates, it's multiple firmwares on your platform. And in many cases I've seen when, as example, embedded controller, just flash it directly to the chip and not authenticated at all. So all of these vectors will be covered on the class. And we will be talk on these details and examples and do some labs on many of them. Another problem is because one-day vulnerability lifetime inside the firmware, it's very long. Because average time of vulnerability disclosure in firmware, it took literally half a year till one or like more year. So what happens, because when you talk with a vendor about the new vulnerability in the firmware, it's not only regarding the fix, it's also the update cycles appears and many other things. And if you think about the firmware update cycle, it's not happens frequently. Most of them, it happens like from 1 to 4 times per year, right? So, and first of all, your fix for vulnerability should fit to update cycle, and it's create really kind of like a not natural but supply chain problem, because vendors created the timeline and environment where the one-day vulnerabilities lifetime is like very, very high. On the other side, the challenges of patching is not easy, and creating the right mitigations and creating the right fix for the vulnerability need to mindset and thinking differently as attacker and not architect. It's why actually many large enterprise companies nowadays and hardware vendors try to create offensive research internally, because they try to cover this gap and meet reality for architects and firmware engineers and hardware engineers. So this connection between reality and your product team is very important, because it's even on design phase and development phase can reduce a lot of risks of potential vulnerabilities in future and create the mitigations more meaningful in the natural way. So yeah, this kind of like a picture show if the hardware is compromised, basically you have everything is compromised. If the firmware is compromised, it can compromise everything higher the stack. Of course, it's very, very simplified picture, and we need to talk more on it during our class. But for now, I want to say it's still relevant. And from the system firmware, even if you can't attack directly the virtual machines, you can attack some of the devices on the platform and try basically attack from them. And think about, you have a lot of them. Modern servers, you have even built-in FPGAs. And if you can attack the bit stream on the FPGA, or like flash your own bit stream, program your own bit stream on FPGA, it's gain a lot of power across the platform. BMC is a key from data center, really. I would say baseboard management controller, known as BMC, is literally a very old concept. And it's still working the same way for years. And basically, in many cases, BMC is responsible for the BIOS update remotely. So basically, if you gain access to BMC, you can attack the BIOS, literally. And it's been shown on the research, which is Alex Gazette and Jeffrey Cherney did on BMC in the last year, presented at multiple conferences. And what they did, they basically attacked the BMC, and from the BMC attacked the BIOS. It's very interesting, and we will be talking about this, and actually we will be do some forensics exercises and labs on BMC during our class. Supply chain attacks on hardware and firmware, it's a growing problem. Think about the attack surface is huge, because like, as I mentioned before, you not get from one place all the hardware to your data center. And this very, very nice picture from Bunny's presentation on the last Blue Hat Israel, it shows in very natural way how the problems can appear. And you have multiple parties involved, which is basically have access to your hardware before it gets to your data center. You have multiple parties which can actually open the boxes and check, as example, custom. And it's not about custom your country, it's about like customs which is passed before it gets to the destination. It can be multiple. I really like Thomas Dooley and Halvar Flake points about signing. Think about. You don't have understanding about what is good, what is bad in your platform, right? And basically, if physical attacker have a control, it's pretty much it. It's about supply chain. But also, another thing which I want to pay attention, we can't check the firmware origin, right? So because what you trust basically what the vendor provide you on website. You trust what is downloaded from the vendor or delivered from the vendor, but you really don't know how it is malicious or not, right? And in many cases, for the hardware vendors, security, unfortunately, not in the first place. We're not talking about the big vendors. We're talking about like the vendors which is produce some small parts like USB controllers and others, or like sometimes it's regarding like embedded controllers. Because it's no vendor who built all the hardware on the platform themselves. It's cooperation between different third parties. And as example, with hardware root of trust, it can be misconfigured because it's very difficult to configure it correctly, or like don't save some way for like recovering the platform. And think about really like if you configure your hardware root of trust ideally, it will be every platform which is breaks, it will be unrecoverable. And you just like call to the vendor and they can't recover, they need to give you new laptop or like new machine. And it's a lot of tied to money risks, which is not acceptable by many hardware vendors. And they try to create the way how they can create some meaningful way to recover the platform. And it's really tied to misconfiguration sometimes. Also, very cool attack being shown by Trammell Hudson this year. It's a time to use, time to check race condition on the SPI Flash chip. Think about, you have read cycles from the SPI Flash chip, which is really different phases read during the boot, different phases can read the SPI Flash chip for some of the assets, as example, ACMs. But sometimes they do it just once and not check it during other boot phases. Basically, we're talking about if authenticated once, that's mean not trust it forever. And as example, on if you check on the very early stage and then don't check and just trust on the later phases of the boot process, it can be faked. And we will be cover this part too. And Intel ACMs and microcode downgrade, and actually also a big problem on x86 because it boots very early, and some of the parts of root of trust for boot guard and BIOS guard, it's tied to ACMs, it's not covered by boot guard. And some of the old platforms have really easy way to downgrade it. So yeah, we have this discussion on the Twitter about the ACMs and microcode downgrade with Alex Yermolov, who actually found some cool stuff on microcode downgrade, and Intel make advisory about this vulnerability. So one more thing from Halvar, it's about the signing problem, because think about the current approach for firmware security is based on trust to code signing. And if you think about what happens in the past, antivirus industry was really trust every binary literally which is signed. But after Stuxnet and after multiple incidents happens with leaked signed keys, with stolen signed keys, so they change their opinions and ways how to detect and classify the malware files or like good files. Why you think it can't happen in the firmware world? I think it's really a scenario which is happening right now, but nobody see it. Third-party components is a part of supply chain hell, and we already talked about that. Because supply chain attacks vectors extend attack surface, which has always been out of scope for the hardware and firmware vendors. Think about the TPM. So Trammel shows how we can basically just soldering on LPC bus or GPIO on TPM chip and try to intercept or fake the signals from it. Jeremy Boone with TPM Genie shows a way how we can create interposer with very simple components. So we will be cover the TPM parts in our training, and we will talk about the threat modeling on TPM, how we can make some audit on TPM configuration on a platform. Nowadays, major vendors, cloud vendors, and hardware vendors like Apple trying to fix the root of problems, basically try to gain more trust to the platform with their own chips. Google have Titan, Apple have a T2, Microsoft develops Cerberus, Amazon Greengrass, but also think about, yes, it's additional check, but in most of the cases, it's very simple chips. And these simple chips have a very simple code inside, and sometimes the code can be not simple, sorry. Boot ROM is simple inside these chips, and sometimes boot ROM can have an issues. What that mean? Most of the cases, it's no memory isolations on this chip. Basically, any code execution on the chip can allow you to develop some egg hunter to dump multiple secrets and things which is stored inside this chip. Yeah, think about that. It's not really a case maybe for Google and Titan, but it's in many cases it can apply on the chips which is used for root of threats on the platforms. And I will be reminded one more time, it's not no any hardware vendors. It's no actually hardware vendors exist which is have a full control on supply chain, which is actually gain very, very serious concerns on the supply chain problems. So operating Shadowhammer, we mentioned it, it's talk about different thing. It was no known information or like public information regarding compromised firmware updates. But think about the same tool, Asus Tech Live Update, was delivering the firmware updates. And basically, the possibility being exist for the attackers. And we really don't know about they use it for deliver malicious stuff on some of the users, what's just targeting or not. But it's very interesting case to keep in mind and demonstrates the power of updating tools, which is basically executes as an engine and persist on the platform. And in many cases, maybe I will be recommend for IT security, don't use persistent engine for the update and use on-demand tools to update the platform what you want and reduce the attack surface for your network. So register to our training and learn more how hunt and reverse engineering firmware implants. Thank you very much.